Okay, hello everyone. So I'm sorry that the recording didn't catch the audio. So I need to do some voiceover. Okay. Okay, the first thing I mentioned in the class is I type f double prime, right, equal to 0. It should be f prime of c equals 0. This is the second derivative test to check the local minimum and local maximum. So we could also using this second derivative test to check the minimum and maximum. Okay, so if you have the critical number and you can find the critical number and you check through your second derivative, if it is positive, then it will be a minimum or local minimum. If it is less than 0, it will be a maximum or local maximum. Okay, now after we get some idea on how to find the first derivative, second derivative, and how to use them to check our functions, our curve, whether it's increasing, decreasing, having concavity changes, or we call the inflection points, and we could find all the critical numbers and so on and so forth. So I think we can start with the example. Okay, let's see the example. F of x equal x cubed minus x squared. Okay, it's a very simple polynomial degree 3. So we could start to solve this. And the question is finding maximum, minimum, the concavity, and inflection point. Okay. So this is basically a typical questions or a typical requirements or components that we need for sketching a curve. So sketching a curve using calculus, at least we need to have all these parts. So finding maximum minimum will result in the interval when the function is increasing, decreasing, and then concavity when it is going to be upwards, downwards, and when the concavity changes, which is the inflection point. And then we could work out our example here. So the first thing that we can do is we need to just derive. Okay, so we find the f prime, which is we are going to do the first derivative. So we have 3x squared minus 2x. So we have this first derivative. Okay, now after getting the first derivative, you could always using the first derivative to check the critical numbers, finding critical numbers, and then finding the interval whether the function is increasing or decreasing. Or instead, we could also check directly the second derivative. So we will have the first derivative and second derivative. Okay, and then after that we can do some observations. All right, now the first thing, okay, I will write some process here to add some notes so you know what requirements you need to have to solve this problem. So first is finding the critical numbers. So to find the critical numbers, we are going to equaling the f prime with 0. Okay, so we are just looking at our f prime, which is 3x squared minus 2x, and equaling those f prime with 0. Okay, now I think this is a very basic example, so we could just take factor x out, so factorize, and we see that we have x equals 0 and x equal 2 over 3. Now these two will be our critical numbers, right? So we could also check the original functions, the questions, and factorize and finding the intercepts. This is also important to confirm whether our sketch is true or not, it's correct or not. So this is the intercept. So we get x equals 0 and x equals 1. This is the intercept that we need to anticipate in the sketch or in the curve. Okay. And then the second process that we need to take is to test our first derivative. So first derivative test, okay? So what we are going to do is we are going to find the interval between or involving the x equals 0 and x equal 2/3, the critical numbers. So we are going to observe this through our line numbers. So I think line numbers is really useful in our situation here. So we just put in our critical numbers 0 and 2/3, and then checking all the points that is possible. Okay, so we are going to check the first derivative, which is x and then 3x minus 2. So we just using all the numbers that possible between these two critical numbers, or let's say from the left interval of 0, between 0 and 2/3, and then right interval, the right interval, which is besides the right sides of 2/3. Okay, and then we check the first one, the left interval, we check -1. We could have positive signs, right? And then the next is the in between the number 0 and 2/3. We could check 1/3. 1/3 put inside it going to be negative, and then if we put 1 for the right interval, we could get the positive signs. Okay, so this positive, negative, positive is indicating our increasing or decreasing functions. Okay, so based on our test, whenever we have a positive value, the function is increasing. Okay, so f prime greater 0, f is increasing, and then f prime less than 0 or negative, the f is decreasing. Okay, so keep that in mind. And from these observations, we can also look at the point where x is where the function is maximum or local max and local min. We see that positive, negative, in between positive, negative, it's a local max, and in between negative, positive, it will be local mean. Okay. You could check also using the second derivative to find the local max, local mean. You will find the same confirmations. Okay. Okay, the third steps, we are going to check the second derivative test. Okay. So we are going to write the second derivative, which is 6x minus 2, and we can say that if we want to find the inflection point, sometimes it goes to equaling the second derivative with 0. Although not all function works like this, but for a simple function like this one, it works. Okay, so we get x equal 1/3. The 1/3, it is expected to be our inflection point. It's supposed to be our inflection point. So we could check the inflection point through the line numbers as usual, and then check the interval, check the signs, left of 1/3 and right of 1/3. So we could check maybe 0, and if we check 0 and check also 1, we got positive and negative, right? Okay, and then this positive and negative signs will give you an overview whether the function will concave upwards or downwards. So if you have a positive f double prime, it will be concave upwards. Okay, so f double prime greater 0, f is concave upwards. And then f double prime less than 0 or negative, the f is concave downwards. Okay. And you could write or sketch the concave. Upwards is like U, the letter U, and the downwards is the opposite of this, the concave upwards. Okay. I hope you remember this concavity. Okay. So now we could draw our curve, so we could sketch and then try identify from all the components we have through the calculus parts, which is the first derivative, second derivative, the interval, the local max, local mean, the inflection point, okay, the concavity. Okay, we could check the curve. Okay, so we put all the critical numbers that's supposed to have, so that this curve have, that is 0 and 2/3, and also 1/3, that is our inflection point. Inflection point, I forgot to write that. So inflection point is when x is 1/3, because at x 1/3 the concavity changes. Okay, the concavity changes. There are some cases that we get like supposed to be inflection point, but concavity is not changed, so it's not inflection point. So inflection point is when concavity changes. Okay. And then we can also check the value of the critical numbers to check the points in y-axis. So we could check when x is 0, it's 0, and when x is 2/3, we need to do some little calculations. But this is just to make sure that we know how to put our coordinates. Okay, it doesn't need to be really exact and precise. Okay, as long as it is proportional and it seems logical, makes sense, is supposed to be true, and that will be fine for me. Okay, so no need to compute really exact or really precise numbers or really correct decimals. Okay, so we have this -4/27, which is, it's around to be around 1/6, so it's really small. It is really small. Okay, we could pinpoint our supposed to be coordinates that when the curve getting the maximum or minimum, and then we sketch the graph. We have increasing on the left 0, and then it's supposed to be decreasing, and then reach out 2/3, right? 2/3 value, which is -4/27, and then from this local minimum, we are going to get through the x-axis, because we have the intercept that is x equals 0 and x equals 1. So the curve will touch that point. Okay, so this is the curve that we have. So we need to make sure to confirm. You could also check with your graphing calculators or graphing website or applications whether our approach for the curve is correct or not. Okay. So the important thing is you need to mention all the necessary points. Okay, the necessary points. For example, the necessary points is in our sketch is the inflection point, like this one, 1/3. So we could write this is inflection point, and then mention also the other coordinates, which is the local max and the local mean. Okay, so as long as you write all these informations correct, it should be okay with me if the question is just asking sketching the curve. Okay. Okay, so the next thing is we are going to discuss more the complete curve sketching. So we are going to include also, aside from primary requirements, which is the local max, local mean, the concavity, okay, the first derivative test, second derivative test. We also need to include other requirements, or we could say the secondary one, like the domain, the asymptotes, and so on and so forth. Okay, so we start with the domain. Okay, domain is very basic, so it's supposed to define the functions where the function is defined. Okay, is there any restrictions? Is there any interval that is undefined? Okay, so this should be a very first identification for a curve. Okay. The second one is the intercepts. Okay, the one that we did before. So we could later confirm that the curve will touch these points, okay, when x is 0 or when f of x is 0, okay? So we need to check whether we have intercepts or not, okay? And then the third one is the symmetry. Symmetry means we are going to check, okay, whether the functions is symmetrical or asymmetrical, or maybe not both of them. So we are going to check, plug in negative x inside the functions. If it is going to revert back to original questions, our original functions, it's going to be an even function. If it is negative of that functions, it will be an odd function. Okay, to simplify it, even and odd, you can imagine a function of the x squared and the x cubed, which is very easy to imagine. I think that's very simple functions like this, the even functions x squared and then the cube, the x cubed, okay? So next thing, the fourth is the asymptote, okay? The asymptote, we already learned the asymptote in the chapter 2, the limit. We have the vertical asymptote, we have horizontal asymptote, right? So to find the asymptote, since we have learned the chapter 2, we are going to implement limit, okay? So let's say x is going to approach a. You can think this x getting close from the left or right of a. So the result of this limit, if the result is infinite or negative infinity, then this x equal a, so x equal a will be equal to vertical. This is our vertical asymptote, okay? Okay, the second asymptote is the horizontal one. So horizontal asymptote will be we can get that by taking x approaching infinity or negative infinity, okay? And the result should be a constant, okay? So we are expecting just a constant result. So we could say that y equal L is the horizontal asymptote, okay? So aside from the known vertical asymptote and horizontal asymptote, we might have the other asymptote we call the slant asymptote. The slant asymptote is it's not vertical, it's not horizontal, it is like a linear, just a regular linear equations that if we try to imagine a rational functions p equal to q of x divided by r of x, okay? This will be written if we can rewrite these forms and take the formula out, and maybe using the long divisions or maybe syntactic divisions, we could write like this. So this mx plus b, usually it will be our slant asymptote, okay? That's the easy way to imagine this, okay? So let me just draw what slant asymptote means in geometrical view. So let's say we have this red line here, linear equations, and then we have a curve, okay? We have a curve, the blue one, like that, okay? And we are going to see that the curve at certain point, when it's going to approach positive infinity or negative infinity, in our case here is positive infinity, it's getting closer and closer to the red line, which is the mx plus b. So we are going to define this in terms of limit. So as x is getting close or getting larger and larger, the f of x subtract with the mx plus b, this will be getting close to 0. Okay? So this is actually the definition of the slant asymptote. So mx plus b is slant asymptote if the limit as x approaching infinity of the f of x minus this mx plus b is equal to 0. Okay, so we get this slant asymptote. Okay, perhaps some example might help. So let's getting you some example. Okay. Okay, so example. Let's say we have these equations. This, let's say, a function x squared plus x minus 1 divided by x minus 1. Of course, the top equations cannot be factorized, so we cannot do anything here unless we rewrite this and look at the results. Okay, we can do the syntactic division. I hope you still remember how to do this syntactic division. So we are going to put all the coefficient of the top equation and divide with x minus 1 is supposed to be x equal 1. So we are going to plug in this x equal 1. And then we get that the remainder is 1. So we could rewrite this as 1 and 2 is supposed to be a line equation or linear, so it's x plus 2. So we could write x plus 2 plus, or here is 1, the remainder, over x minus 1. So you could rewrite like this, or if you feel maybe not sure on doing this syntactic division, you can do this long division. So basically just divide x squared plus x minus 1 with x minus 1, like our regular divisions, I think. So we can also get this true, and we get the same results. Actually, we get the same results. Okay. So this x plus 2 is our slant asymptote. Okay, so we could get this from the syntactic divisions or a long divisions, but remember to go back to the definitions of this slant asymptote, which is the limit as x going to infinite of the subtraction between fx and mx plus b is equal to 0. Okay. Okay, so after the asymptote, another thing that we already learned before in the previous page is the increasing, decreasing interval. So this is related to the first derivative, right? So we are going to have f prime when it's positive, or we call this is the f prime test. So f prime positive and f prime negative. Okay, this is related to the increasing when it's positive and decreasing when it's negative. Okay. Okay, next is the local max and min. This is we get this through the critical numbers, and we put the critical numbers to get our max min value. Okay. So we take the f prime equals 0 to get the critical numbers. So find the critical numbers. That is. So this two increasing decreasing interval and local max min is going to be works together. Okay, so we find critical number, we check the line numbers, we find the increasing decreasing interval. Okay, and that's it. Okay, the next part is the concavity. Okay, and the inflection point, which is related to the second derivative test. Okay, so the second derivative test, okay, will conclude the concavity. Okay, will resulting in the concavity observations. So when the f double prime positive and f double prime negative, the concavity will be changing. So when it's positive, it's concave upwards. When it's negative, it's concave downwards. Okay. So you can see the shape. Okay. So I hope you remember how it looks like, how the shape looks like. Okay. So the inflection point is supposed to be the f double prime is equal to 0, but it's not necessarily to be 0 as long as the concavity change. That's the idea, okay, for the inflection point. So let me write. It's not always equaling to 0, the inflection point. Okay. So the inflection point is the point when concavity change. That's it. Okay, let's getting some examples. So let's sketch the curve of functions 2x squared over the x squared minus 1. Okay, so we could start these questions by taking sometimes to like the previous page telling us. We could start from the very beginning, from domain intercepts. Okay, or we could directly go through the first derivative, second derivative. That's okay, as long as we still on track. Okay, some questions may require to include all the writings, okay, like finding the interval, something like that. But some other questions just focus on the final results of the sketch, how the sketch looks like. Okay, so first we could check the domain. Of course, it is obvious that because we have the rational function with something on the bottom that might undefine on some interval. So we could start to check. So we could write down the x supposed to be or not to be plus minus 1, because that will be undefined, and all other x will be defined as real numbers. And we could also check the intercept when x is 0. Okay, we could plug in x equals 0, and we get it's actually 0. So 0.00 are our intercept. So it will be going to have a 0.00 in our curve, and this will be our intercept. Okay, so the symmetry we could check through the plug in negative x. So we could check that way, and we find that it's going to be the same equations as the original equations, which is going to be even functions. So I think I miss out why I'm writing the it's supposed to be minus, but I'm right equal sign. Okay, whatever. Okay, now the asymptote, we could start with the one that obviously can be seen from the equations is the from the domain. Okay, so we could start from there. So we could start with the finding the limit for x approaching 1 of the functions, and I think we could get the conclusions that this x equal 1 will be our vertical asymptote, right? Okay. And the same thing also for x approaching -1. So we could do from both sides, okay, from the left sides, approaching from the left side or approaching from the right side, as if we have done in limit. And if the result is infinity or negative infinity, then these two lines will be our vertical asymptote. So x equal 1 and x equal -1, that will be our vertical asymptote. Okay. Okay, the next thing is finding the horizontal asymptote. This is getting through by the if we approaching limit to infinite or negative infinite. Okay, I think we have done this before. So if you have 2x squared and then the bottom one is x squared minus 1, the highest polynomial degree is 2, so we are going just to focus with 2 and 1, so we have 2 as our result. So y equal 2 will be our horizontal asymptote. Okay, so we could write this as our horizontal asymptote. So you could continue this at your home and finding the other parts as well, and then sketch the curve at the end. Okay, and then also adding another example for you to check at home. I'm giving you this function 1 over x squared minus 1 over x minus 1 squared. So you could check this out. So sketching this curve. Okay, you could check also from the graphing calculators or website like GeoGebra, Desmos, or any website you know of, and then compare with your calculus parts. Okay? And then this is actually quite difficult, but you can try. Okay? Okay. We're going to continue. Okay, so this part we are going to continue next week, and you could also try triangle in this function, sketch this function. Maybe before you start, you could check what kind of graph you could have from this, right? Maybe GeoGebra or any apps you have. I think your tablet or the phone you will have some calculator for graphing. I think there will be some apps. Right? I think GeoGebra, Desmos, and maybe Wolfram also. You can check how it goes and try using calculus to do your own part. Well, it's not easy. This function is not easy. Yeah, not easy. Not easy. Could you imagine if you derive and then the second derivative and then finding the test equaling to 0, and it's not easy. Even for me, not easy. I mean, not easy because it's not difficult, but it's long. It's long, yeah. Okay, I think we are going to review our homework. Okay, our homework just a few parts that. I think I'm going to start from the very bottom. Not very bottom. Maybe number 4, the related traits first. And after that, the very bottom. And let's do two questions from the bottom parts of the question. Okay, first is I think number 4, right? Number 4. This is the spotlight, so related rates. The spotlight problem. I think the problem here is to understand the question, how to determine the point. So you are given the triangle. Okay. And you have the man walking. Let's say it's the man. Okay. You have the lamp here, the spotlight. And then you have the man is 2 meters tall, right? And then we are not sure that the wall, but just name wall is y, and then this one will be maybe x. 12 minus x. The question already given this information, right? So when the spotlight goes through here, it will cast a shadow, right? So when the man is walking, the question is asking when the man is walking with some fixed rate of t, which is the we say it's I think 1.6 meter per second, how the shadow that cast by the spotlight increase. Okay? So which means that it's actually this one. So because the shadow is supposed to be casted that way. So first is finding the relations. So let me go through the information. So the information is dx dt is 1.6. Okay. And then the relations from the triangle, we got y over 12. Okay. So let me describe this x is from here. This 12 minus x is from here. So the total is 12. This is equal to 2 over x. So we are going to have y equal 24 over x. Okay. So I think with this only formula, I think we could get the answer. Okay. So let's derive this and make our related rates formula. So derive with respect to t, and we are going to get, this will be minus, right, x squared, and then dx over dt. Now, the question is asking dy over dt when the man is, how many? The man is 4 meters from the building. So which means that 12 minus x is equal to 4. Okay, 12 minus x is equal to 4. So which means the x is 8. Okay. So when, because this is the building, right? This is the building, the wall, right? So when 12 minus x equal 4, x is equal 8. So dy over dt is equal negative 24. This will be 8 squared, right? And dx over dt is 16 over 10, so we can cancel this out. So we have 6 over 10. So it's negative 0.6. The negative means it's decreasing, okay? Decreasing 0.6. So this is decreasing. Okay, maybe the question's kind of difficult to understand because of these 4 meters. Is this 4x or this 1, right? But the question is actually telling us that the man is 4 meters from the building. Okay? And where's the building? I think the question is only given this is as the building. There is no other building in the question. The original questions, it doesn't include this triangle. So it's more difficult to understand. So I'm giving you the triangle to help you understand at least how to find these formulations between the triangle congruency. Oh, this is, oh, forgot the S. Okay. Okay, so I think if we are going to solve another related rates problem in exam, I'll give you hint and also the picture so you can have more understanding on the question itself. And I will maybe write the questions and maybe make simplification for the terms. Sometimes if the terms, like for example, like altitude, maybe some of you are not really well known that altitude is the same as height. So I think I was just using this the easier terms for you so you can understand the question more. All right, number 4. Okay. Let's move to number 5. The last two. This is the last two, right? We are going to find the f prime x, and we are given that d dx of the f2x is equal to x squared. Okay. Okay. Now always remember, every time you see an equations or any calculus problem that has this d over dx, it means that this is a tool to derive, right? This is tool to derive. So every component inside this bracket here with this dx outside, it means that we are going to derive everything inside here. So we are going to derive f to x with respect to x. Okay. So we could write this. Let me use the different color. We could write this as usual. Well, you could think maybe just like usual x, or maybe, but if you have x, it's not really good example. But any other functions that we have, if we remember how the chain rule works, this is the chain rule. So we are going to f prime to x multiplied by the chain rule with 2x derived is 2. Right? So we are getting that this will be. Let me write one by one. Okay. So we could write that f prime to x is equal to half x squared. Okay. But our objective is f prime x, not to x. So how do we do? How do we proceed? Now we proceed with, we are going to equaling this to any variables we can think. We can think like a dummy variable p. Usually p is a dummy variable in calculus. You will see maybe later, maybe next semester in calculus, we are going to use p a lot. So we are going to let this 2x equal to some p. So let t is 2x, so x becomes half t. Now we define this and we get that f prime t is half, which we get that this is going to be 8, which is equivalent with our f prime x. So this dummy variables is actually one way to simplify our calculations also. It can help us to maybe simplify any, like when you have like higher polynomials and you want to simplify with the lower one, the more simple in the computations, we can do that also. Like in limit, also we can also simplify limit. Like for example, we usually have the x to infinity. Sometimes we are going to have like, let x is 1 over t, and then the x could be changed to t, and then t will be equal to 0, rather than approaching infinity for limit.
So we have to follow the chain rule.
Yes, chain rule. So this is chain rule from this is chain rule.
Why does the 19 become the x?
T is any variable, right? It's any variable. And I'm defining that t is this 2x. So when we have f prime t, this t can be any variable, right? If we change to getting x, then this will be 1 over x, right? Okay. And this is as simple as that. It can be any variable. And I think the next questions that I would like to emphasize is from the first question, which has a lot of derivative computations, right? I think the last part for number 1, right? It's kind of complicated. But I would like to well, any requests from you? Which part? For sure, the last part on number 1 I will explain later. But is there any from the previous one? I checked some of you, and I think you already did a good job. But maybe just some suggestions. Yeah, any requests? Which one? Any requests? No? Okay. Let me start with okay, maybe start with this. Okay. So if we have ln, okay. Okay, now to solve this, we are going to do some implicit differentiations. Okay, but remember, when we have this ln and we have this fractional function, my suggestion is to separate them first, and then you can differentiate. Because if we separate this, become ln x minus ln y, that will be a simplified form, right, to be differentiated. So let's do that first. So this will be ln x minus ln y. This is equal e xy. And now we can integrate, not integrate, differentiate. We are not done yet for the integration. So this will be 1 over x and then 1 over y. And don't forget, every time we've done with y, we add dy over dx. And then the right part, we see e, right? Remember, e, if we differentiate, we will have the same original equations and then multiply with the chain rule. So let me write the chain rule. Okay. And don't forget that since these two are implicitly related, and they are each one of them are a function, then we need to check this through the product rule. So we're going to have a product rule. So let's say this is fg. So this will be 1 over x minus 1 over y. So let's say this is y plus x and then dy of dx. Okay. The next thing is to grouping all together, finding the dy over dx. So we are going to have okay, I will move this to the right, but I will write on the left. Okay. And then the same thing with the other one. So I will write dy over dx and then 1 over y plus x e x y. And the right side will be 1 over x minus y e x y. And then dy dx is equal the rest of this solutions are just simplify the forms. You can stop until here, or you could simplify it again to become more clean forms. So let's multiply with xy over xy. So we multiply with this. So we get that dy over dx is y minus xy squared exy. This is x plus x squared y xy. Okay. Well, you can just stop until here. It's still okay. Okay, but if it's an exam, still also complete points. Unless maybe the question giving you options that you need to choose carefully. And sometimes when you have done here, you cannot see the option. Where is my answer? But still, you still get point. Yeah, not complete. Maybe 85%. Also for the first one, you have polynomials and over square root of x, right? Some of you directly using the quotient rule, that's okay. I think some of you also, you define one by one and then differentiate. I think that's more easier. I think that's more easy. That's, okay, yeah, please. I just startled. I thought like, okay, it's gas leaking. I think the last part on number 1. I see a few students, they really got the process, but not finishing. Maybe it's way complicated. But that's okay. That's okay. I will show you and give you some suggestions what to do. Okay. Okay. Yeah. This is. The process is actually easy to understand, but when we wrote the simplified form, the algebraic form, the operations, it's difficult. We can also write this as a tangent inverse, right? The arctangent, to just reminding you what it is. Okay, remember, if we have a tangent inverse, let me give you an example here. If you have this is 1 over 1 plus x squared, and it's good thing to have. So this is going to be y prime. This is 1 over 1 plus all the things here and it's squared, so it's become 1 minus x, 1 plus x. Okay, and then differentiate this thing here. All the things 1 minus x, 1 plus x. Okay, maybe using different color. Now let's solve this in the x over 1 and let's simplify this first. Let's simplify. So let me use red color to give you an overview. So we see that we will have 1 over 1 plus x So we are going to simplify this and make it 1 plus x. Okay. So 2 over 1 plus x, right? Or 1 plus x over 2, we going to up. So this will be equal to 1 plus x over 2. Okay, this is from 2 over 1 plus x. Okay, and then we move the 2 over 1 plus x. We reverse, and we get this. Okay. All right. And then we derive this. Remember, okay, when we have the square root of x, this first derivative is 1 over 2 square root of x, or we could say half x minus half, right? So let's write that first, and then make another chain rule. Okay? So as long as you keep patient, steady, I think you'll finish these equations. Okay? So this will be 1 over 2, and then this will be 1 minus x, 1 plus x, minus half, and then the rest is d dx of 1 minus x, 1 plus x. Okay? Still, we are going to, well, if you feel not really confident doing in one paper, so we could move to another paper to calculate this. So let's say this is becoming 1 plus x squared, and then this will be minus 1 plus x, and minus of 1 minus x. And this will be result in negative 2 plus 2x, right? And this will be 1 plus x squared. Is it okay? Oh, no. It should be 0, right? It should be 0, so sorry. Okay, and I think this is a good number. This is a good number. So we're going to have 1 plus x over 2, half, and then we have this. And we have negative 2 over 1 plus x squared. We can cancel this with this. And we have 1 over 2. And then the negative 1, okay, negative 1 over 2. And then multiply with, or maybe we could write, we can cancel this first. Yeah, we can cancel. So we have 1 plus x. So let me write one by one here. So this will be 1 minus x, negative half. So this will be 1 plus x, negative half, plus 1. Okay, so we will have 1 plus x half, right? So we are going to have 1 plus x half. This is really good, simple, right? But I'm not done yet. I will make it more simple. I will move this to the denominator. So we are going to have, first is 1 minus x, and the other one is 1 plus x, like that. And we can multiply all together. So we have again, I put options and I hit this in the option. It will be written. So I think this kind of question is taking time. It's good for exercise, but if I'm giving this in the exam, it will be unfair, right? Because it's taking too many times. Yeah, taking too many times. a question that really good in exam is simple, but you need to think. Like maybe the answer is short, but how to get that short answer is you need to think maybe more than usual, and that's very good. Okay, I think we can have one more. Oh, also, the number 3, if you check number 3, it's asking you to find the point where the tangent is horizontal, right? I think a lot of students, they assume the interval maybe just from 0 to pi or 0 to something, but actually it can be rotated all over. So you need to make sure the answer. So if you just answer x is 0 or x is pi over 2, x is 3 over 2 pi, it's not a complete answer. You need to also consider plus 2 pi n, okay? Because if you can rotate more, it can also be another solution, right? So that's one thing. Unless the questions may be giving you the interval, okay? Then you can directly answer like that. Okay, any questions? Maybe any requests which part? I will give the rest, the answer key later.
Can you discuss about yesterday's Mentimeter quiz?
Ah. Okay. Let me check the questions. Check my Mentimeter. Hopefully still have time. Yesterday Mentimeter. Okay, this is for what question? Okay. Oh, I see. Okay, the kite, right? Yeah, I think there is something wrong in the questions, okay? We'll later give you the correct answer and the correct winners.
Which one was correct?
Let me check. So it's supposed to be, so the kite questions is, you have, I'm giving you this like theta, you have y, you have x, and you have 50, right? And I think the question is said that when y is 200, and when the string is 200, right? It's supposed to be 100. So there is some mistake on the question. So I will revise the questions and revise the answers and let you know how it feels. So it's actually taking the, so we have the x dt is 2 meter per second, right? We have the cotangent theta is x over 50, and x is 50 cotangent theta. So we take this derivative and we get, this is going to be cosecant theta d theta dt, and you will get that d theta dt will be negative sine squared theta over 50 multiplied 2. So it's supposed to be when y is, it's supposed to be y 100, not 200. But your question is y is 200, right? Right? It's supposed to be 100. Really sorry for that. Because I'm using two different textbooks. One is using feet, which is 200 feet. The another one is 100 meter. So yeah, so that's. But actually the same question. So I mix up the whole numbers. Okay. So if this is 100, if y is 100, then we are going to have this 100. Then the sine will be sine theta will be 50 over, or maybe we could write with 200 first. So 50 over 200, this will be 1 over 4. Okay, so this will be negative 1 over 8. So it should be 200, 1 over 200. So there is no answers, right? I think no options, right? Yeah. So I will give points to all people. Yeah, it's supposed to be 100. I mix up the feet.
100 is what is the correct answer?
It should be radian per second.
So with 100 is twice less, yeah? The correct answer.
1 over 100 is supposed to be, but
Yeah.
if we are using this number, we have 1 over 200. Yeah.
Yesterday we used 100 and we got 1 over 100. Yeah.
Oh, you use 100?
On the lunch, yeah, we
Yeah.
tried to discuss it. Yeah.
Yeah, so this is the mistake. Okay, so all of you will get a bonus. The more you have. Okay, if there is no more question, is there any questions left? So next week we'll continue the chapter 4, the sketching curve. Next week, and going through the indeterminate forms, the L'Hopital rule next week. And also, if we still have time, we are going to have additional optimization. It's actually the same thing what we have done with maximum minimum value. That's the optimization. So when we have done that next week, so the second week, the next 2 weeks, supposed to be the meter. Okay? But if we still have more exercise in next week, then perhaps it will be the third week. Okay? So please be aware, if we done the optimization next week, then after that it's supposed to be your midterm. So to help you with that, I will give you exercise and last year or maybe last 2 years samples for midterm. So you could work on that. Okay, now if there is no other questions, we are going to the feedback now. Okay, and hopefully I didn't make any typo or mistake. Okay. 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 This is yesterday. Which one? This one. So it's supposed to be chapter 4. Okay, chapter 4. So the application. Okay. I think I have 2 questions. Each question maybe around 1. I think 2 minutes. 2 or 3 minutes. I think should be enough. Should be enough. It's not really heavy complicated. Should be easy. Okay, have you? Okay, we are going to start. Okay, if you miss out this QR code, you can join through the website. Okay, I think we can start. For number 1. A little bit calculations. I think you should be able to get this one. Remember that whenever you find maximum minimum value, one thing to know is finding the critical number. Check the critical number. And if it has the interval, check the interval. Sometimes the interval is the answer. But generally the answer should be the critical number. But sometimes in the interval, you should check it. Well, you could use calculator if you want to check the numbers. I think the time is too short. Really sorry for that. Okay. So minimum means the lowest one, the lowest point that you can get from all possibilities. Yeah, the one on the top. The lowest. You can check with calculator. You can check with calculator. -3. Okay. So you need to check the endpoints. Okay. If you have the interval, don't forget to check the interval. Okay, last one. No, haven't. Oh. Okay. Skip the questions. Finish. Yeah. Okay. So skip the question. I will continue the question next week. I don't know. I think I removed it accidentally. Okay. Okay. So sorry about that. I accidentally removed it. Okay, so if you finish, so see you next week.